descent silently rising through the thick atmosphere into the boundless night, bound for a destination unlike any other, 15 million kilometers from Earth, at a place where the gravity of the Sun and Earth perfectly cancel out. It came to rest, suspended in celestial equilibrium at the second Lagrange point. This was no ordinary observatory. It was a gateway to the deep past. There, in the cold vacuum of space, the James Webb Space Telescope slowly unfolded, like an origami flower blooming in zero gravity. Golden hexagonal mirrors clicked into alignment. Delicate sunshields stretched out like wings to block the harsh solar glare. And the observatory cooled, waiting, listening, watching. After decades of design and $10 billion of international collaboration, it was time a signal from Earth awakened the telescope's instruments, and at last, after years of anticipation, Webb opened its golden eye and began to see. What it saw changed everything. JWST, with its infrared gaze, was built to do many things: peer into stellar nurseries, study alien worlds for signs of life, and trace the faint afterglow of cosmic birth. But its most astonishing revelations came when it turned its attention to the very beginning, the first billion years after the Big Bang. Astronomers had long predicted what the early universe should look like, according to the Standard Model, our cherished lambda cold dark matter framework. The cosmos began small and simple. Galaxies were supposed to emerge slowly, assembling through countless mergers of smaller structures. They should have been faint, irregular, and primitive. But JWST revealed something startling. In the haze of ancient light, it found fully formed galaxies, large, luminous, structured, far too massive, far too early. They stood like ancient cities in the wilderness, monuments built in cosmic time, too short for such architecture. According to our best theories, they shouldn't even exist. For some, this was a call to update our models of star formation and early cosmic evolution. For others, it was far more unsettling, a crack, perhaps, in the foundations of modern cosmology. Could it be that dark matter behaves differently than we thought? Could dark energy, or even the fabric of space-time itself, be changing in ways we have yet to understand? This would not be the first time the universe has surprised us. From Galileo's first glimpse of Jupiter's moons to Hubble's discovery of an expanding universe, every new instrument has rewritten a chapter in our cosmic story. And now, with the James Webb Space Telescope casting its eye further into the past than anything before, we are once again at the threshold of discovery. So, what do these ancient galaxies truly tell us? Are they anomalies? Outliers to be explained? Or are they messengers from a deeper, more complex truth? This is the story of the universe's first great structures, the story of the galaxies that weren't supposed to be there, and the story of a telescope that may just change everything we thought we knew about the beginning of time. Eyes to the heavens. To gaze upward is to engage in an ancient ritual, a tradition as old as our own intellect. But the transformation of that gaze into a disciplined exploration began in earnest 4 centuries ago, when Galileo Galilei first pointed a telescope toward the night sky. Though the telescope had only recently been invented, primarily as a tool for earthly pursuits such as navigation and warfare, Galileo redirected its purpose toward the heavens. In doing so, he planted the seeds of a scientific revolution. With nothing more than a simple configuration of lenses, he observed the phases of Venus, the moons of Jupiter, and the pockmarked surface of the moon, shattering the long-held notion of celestial perfection. A few decades later, Isaac Newton took the next logical leap. By replacing lenses with a curved mirror, Newton eliminated the chromatic aberrations that plagued refracting telescopes and created the prototype for the modern reflector, laying the foundation for today's colossal observatories, including the James Webb Space Telescope. Newton's mechanical insights into optics may not have directly transformed astronomy, but his universal laws of motion and gravitation reshaped our understanding of celestial mechanics. The orbits of planets, moons, and comets were no longer seen as divine choreography, but as the natural consequence of mathematical laws, elegant, immutable, and pervasive. As telescope technology improved, so too did our ability to collect and refine the light of the cosmos. With each refinement, longer focal lengths, larger apertures, better mirror coatings, the universe revealed more of its grandeur, more of its complexity. By the mid-18th century, French astronomer Charles Messier was among those using telescopes to hunt for comets drawn to their glowing comas produced by the sublimation of ice and dust as they neared the sun. But Messier's work was repeatedly interrupted by fuzzy, unmoving smudges in the sky that did not behave like comets at all. These interlopers didn't move night to night. They refused to perform as expected. To avoid wasting time, Messier began cataloging them, curating a list of distractions, most of which turned out to be nebulae or star clusters within our own galaxy. Yet, unbeknownst to Messier, some of these faint objects were far more distant, entire galaxies in their own right. Through the 19th century, telescopic enhancements revealed structure in some of these enigmatic smudges, spiraling arm symmetry rotation, suggesting they were more than gas clouds. These visual cues led to a growing debate: were these spiral nebulae part of our own Milky Way? Or were they island universes, external galaxies far beyond our stellar neighborhood? This central question culminated in the great debate of 1920 between Harlow Shapley, who believed the Milky Way was the entire universe, and Heber Curtis, who argued for a far more expansive cosmos populated by myriad galaxies. It was Edwin Hubble who ultimately settled the matter, using the 25-meter Hooker telescope at Mount Wilson Observatory. Hubble resolved individual stars in the Andromeda Nebula and determined its distance via Cepheid variable stars. The results were staggering. Andromeda lay well beyond the Milky Way. Not only was our galaxy not alone, but the universe was vastly larger than previously imagined. And more still, Hubble discovered that nearly all galaxies are receding from us, their light stretched into longer, redder wavelengths by cosmic expansion. In a few short years, the universe had gone from a static stage to a dynamic, evolving entity, a cosmos that was born in a fiery beginning we now call the Big Bang. This monumental realization sparked new questions. If the early universe was hot, dense, and nearly uniform, where did the vast structures we see today originate? What mechanisms sculpted galaxies from that primordial smoothness? As telescopes continued to grow throughout the 20th century, both in aperture and technological sophistication, astronomers pursued these questions deeper into the dark. Earth-based observatories pushed the envelope with mirror diameters reaching 10 meters, allowing them to pierce through layers of dust and reach fainter, more distant light. But they were ultimately limited by Earth's own atmosphere, whose constant turbulence blurred incoming starlight. The solution was to escape the atmosphere entirely. In 1990, the Hubble Space Telescope was launched into low Earth orbit, carrying a modest 25-meter mirror but free from atmospheric distortion. The clarity of its images transformed both science and public imagination, producing iconic photographs of galaxies, nebulae, and deep cosmic vistas that adorned both academic journals and classroom posters around the world. But science does not rest on its achievements. Even before Hubble had reached full operation, plans were underway for its successor, a telescope that would peer not merely into distant galaxies but into cosmic history itself. The James Webb Space Telescope, a marvel of modern engineering, was envisioned to carry a 65-meter segmented mirror far too large to fit into a rocket in one piece. Like some vast piece of origami, the telescope would have to be folded for launch and delicately unfurled in space. Its destination was not Earth orbit, but a gravitational perch 15 million kilometers away the Sun, Earth Lagrange point L2. There, in the frigid silence of deep space, it would be shielded from the Sun's heat by a 5-layer sunshield the size of a tennis court, cooled until it could detect the faint infrared glow of the earliest galaxies. After decades of delays, cost overruns, and technological challenges, JWST launched on Christmas Day 2021, riding atop an Ariane 5 rocket and carrying with it the hopes of an entire generation of astronomers. Its mission to chart the life cycles of stars, to study the atmospheres of distant exoplanets for signs of life, and most ambitiously to search for the first galaxies ever formed to witness the dawn of structure in the universe. What it would find no one could say for sure, but one question loomed large. Where did galaxies come from, and when did they arise in the cosmic timeline? The answer lay in light that had traveled for over 13 billion years, emitted by stars and galaxies that lived and died long before Earth even formed. As James Webb opened its golden eye to the deep sky, it began collecting this ancient light, offering us not just a glimpse, but a new window into the formative epochs of the cosmos, one capable of changing everything we thought we knew. The first galaxies. To understand the first galaxies, we must embark on a journey not merely through space, but through time, reaching back across the eons to a cosmos still unformed, still raw with potential. The tale of these primordial structures begins with a paradoxical fusion, a story that connects the largest scales of the universe to its smallest weaving together, the tapestry of galaxies from quantum ripples in space-time itself. Our modern tools for exploring this tale are many, but one of the most transformative is the Planck satellite launched in 2009, and for a time, the coldest known object in space. Its mission was not to observe stars nor even galaxies. Instead, Planck mapped the entire sky in exquisite detail, focusing on the cosmic microwave background, the afterglow of the Big Bang. This radiation is ancient, stretching across the universe at a uniform temperature of roughly 273 degrees above absolute zero. But within that uniformity lies the key to cosmic structure: tiny temperature fluctuations, 1 part in 100,000, representing the earliest imprints of gravitational variation. These ripples were not random. They originated from quantum fluctuations during an extraordinary event known as cosmic inflation, which occurred just a fraction of a second after the Big Bang. Inflation magnified microscopic fluctuations to macroscopic scales, imprinting space itself with density variations. When inflation ended, these frozen quantum disturbances were filled with energy, becoming the seeds of galaxies yet to form. As the universe cooled, particles condensed. Within the first microsecond, quarks were locked into protons and neutrons. After a few minutes, these fused into the first atomic nuclei, mostly hydrogen and helium. The fires of primordial nucleosynthesis burned briefly but profoundly, leaving behind a smooth sea of atomic matter, now expanding and cooling through time. Yet for nearly 100 million years, the cosmos lay in darkness, a period aptly named the Cosmic Dark Ages. Though matter existed, no stars had yet formed to light the skies. Still, gravity worked silently, shaping structure through the invisible scaffolding of dark matter. Unlike ordinary matter, dark matter does not interact via light, but its gravitational pull is immense. It began to collapse into overdensities, regions where matter was slightly denser than average. These overdensities grew and merged, forming the first dark matter halos, gravitational wells into which ordinary matter would later fall. Ordinary matter, hydrogen and helium gas, responded differently. It could cool, compress, and radiate energy, unlike its dark counterpart. Eventually, as gas settled into these halos, it began to fragment. The densest fragments collapsed under their own weight, and in their cores, temperatures rose high enough for nuclear fusion to ignite. Thus, after a cosmic slumber, the first stars flared into being. These stars, known as population 3 stars, were fundamentally different from the stars of today. They contained only hydrogen and helium, lacking the heavier elements, what astronomers call metals, that are forged in stellar interiors. Without these metals to aid cooling, these early stars grew to tremendous sizes, often exceeding 100 times the mass of our Sun. They burned hot and bright, emitting intense ultraviolet radiation, but their lives were brief, just a few million years before ending in dramatic supernova explosions or collapsing directly into black holes. With the birth of these first stars came the epoch of reionization. Their powerful radiation ionized the surrounding neutral hydrogen, stripping electrons from atoms and transforming the universe's dark plasma into a transparent, glowing cosmos. This transition, marked by growing bubbles of ionized gas, signaled a universe awakening. Yet the story of the first galaxies had only just begun. Stars do not form in isolation. They cluster their gravitational attraction, drawing them into associations. The early universe seeded with these dark matter halos, and increasingly enriched with metals from supernovae, began to assemble the first proto-galaxies. But defining a first galaxy is not straightforward. Unlike stars, which ignite in a discrete event, galaxies evolve gradually. They grow through accretion, the slow gathering of gas, and through mergers where smaller systems collide and combine into larger ones. What we observe today as majestic spirals and giant ellipticals began as modest knots of matter coalescing under the persistent influence of gravity. These formative galaxies were not all successful. In the smallest halos, a single population 3 star could disrupt the entire system. Its supernova might expel all remaining gas, halting further star formation, and leaving behind a dark halo, what we call a dark galaxy. Such ghostly remnants may still drift unnoticed through the cosmos. However, in larger halos, gravity prevailed, gas was reaccreted, and successive generations of stars began to form. These newer stars, now enriched with trace amounts of carbon, oxygen, and heavier elements, were markedly different from their predecessors. The presence of metals altered the opacity of stellar material, affecting how energy moved through the star and changing its evolution. Stars, like our Sun, with lifespans of billions of years, became possible. Thus began the transition from the first galaxies to the galactic zoo we observe today. The most massive halos continued to grow, attracting and merging with others. This hierarchical buildup is a cornerstone of the LCDM model, our best current theory for the structure of the universe. But not all galaxies grew at the same rate. Some remained small, fragile collections of stars, while others ballooned into giants. As mass increased, so did stability. Larger galaxies retained their gas even after supernova, supporting sustained star formation across cosmic time. These galaxies became cosmic engines, generating light metals and structure on ever larger scales. Meanwhile, as stars aged and died, the heavy elements they produced were dispersed, enriching the interstellar medium. This chemical evolution is crucial. Without carbon and oxygen, there would be no Earth, no life, and no astronomers to tell this story. What began as imperceptible quantum ripples now echoed across billions of light years. The cosmic microwave background, once uniform, had evolved into a universe populated with galaxies, each a complex ecosystem of gas stars, black holes, and dark matter. And though we can simulate much of this history with remarkable precision, observations always bring surprises. The James Webb Space Telescope, Our most powerful observatory to date has begun to peer into this epoch. Already, it has challenged expectations, revealing galaxies more massive, more structured, and more numerous in the first billion years than theory had predicted. These findings do not undermine our cosmological framework, but instead sharpen it. As in all science, anomalies are invitations, prompts to revisit assumptions, refine models, and look deeper. The early universe is a frontier not only of time and distance, but of knowledge. We stand now at its edge, our instruments pointed skyward, seeking in the ancient light the answers to questions formed by the fusion of curiosity and reason. The first galaxies were not monumental in size nor grand in appearance, but they were monuments of process evidence that gravity, chemistry, and time, guided by the laws of physics, could sculpt the void into luminous form. From the tiny ripples imprinted in the quantum fog of the early universe to the brilliant spirals now wheeling across our skies. This is the journey of structure, of complexity, and ultimately of us. For somewhere in one of those fledgling galaxies, a sun would one day rise, and orbiting that sun, a small rocky world would look back at the stars and wonder how it all began. The Galactic Zoo. In 1932, amidst the dawn of global radio communications, a peculiar discovery emerged not from the optical lens of a telescope, but from the static of a radio receiver. Carl Jansky, an engineer at Bell Telephone Laboratories, was investigating sources of interference in transatlantic radio signals when he noticed something strange, a persistent hiss of background noise, faint but measurable. Initially, he attributed it to terrestrial causes, perhaps lightning or electrical equipment. But the mystery deepened when Jansky observed that this static did not align with the rhythm of Earth's 24-hour solar day. Instead, it shifted ever so slightly, adhering to a cycle just under 24 hours. Sidereal time, the time taken for distant stars to return to the same position in the sky. This seemingly minor discrepancy of 4 minutes per day carried profound implications. It meant that the source of this radio interference was not of earthly origin, nor even tied to the sun, but came from well beyond our solar system. Jansky had inadvertently detected radio waves from the Milky Way itself, the first ever confirmed reception of electromagnetic radiation from deep space outside the visible spectrum. This serendipitous moment marked the birth of radio astronomy. Although Jansky himself was redirected to other duties and did not pursue the discovery further, his name became immortalized in the field. Today, we measure the strength of radio emissions from celestial sources in Jansky's. Others picked up the mantle. Notably, Grota Reber, a young engineer and amateur radio enthusiast, constructed the world's first purpose-built radio telescope in his backyard. For a time, he was the only practicing radio astronomer on Earth. Through his work, Reber confirmed Jansky's findings and revealed that the Milky Way emitted radio waves across the sky, opening a new window onto the cosmos. Soon as radio telescopes proliferated and improved, astronomers discovered more than just emissions from our own galaxy. They detected incredibly powerful radio sources, compact, bright, and seemingly point-like, that emitted energy on a scale difficult to reconcile with known stellar processes. These mysterious objects came to be known as quasi-stellar radio sources, or quasars. Appearing star-like in optical images but blazing with radio energy, quasars were later understood to be powered by supermassive black holes, some with masses exceeding 1 billion suns, feeding on surrounding matter and releasing enormous amounts of energy as they accreted gas and dust. These beacons could be seen across billions of light-years, revealing not only their own immense power, but also illuminating the early universe itself. Quasars represented just one expression of the intense activity that characterized the first few billion years of cosmic history. During this primordial epoch, the universe blazed with light and change. First stars ignited, first galaxies assembled, and first black holes fed ravenously. But as the universe aged, the youthful fervor of cosmic activity waned. Star formation began to slow, and galaxies matured into more stable configurations. Yet even in this apparent calm, gravity continued its work, relentlessly driving evolution on every scale. Galaxies, like living organisms, changed with time. Small galaxies merged and coalesced into larger ones. Larger galaxies in turn consumed their surroundings and grew more massive still. Some galaxies developed distinct structures shaped by their internal dynamics. Disc-shaped galaxies like our Milky Way spun into elegant spirals, their rotation sustained by the conservation of angular momentum. Cold gas within these spinning disks collapsed into stars, forming the grand design spirals that populate astronomical catalogs today. Other galaxies suffered more turbulent fates. Violent mergers between massive galaxies often disrupted their ordered rotation, transforming them into chaotic amorphous systems known as elliptical galaxies. Lacking the structured spiral arms of their cousins, these spheroidal galaxies contain older stellar populations and less gas, signaling the end of vigorous star formation. The cosmos thus revealed a dichotomy in galactic morphology: spirals and ellipticals, each reflecting distinct evolutionary pathways shaped by collisions and environmental interactions. Yet not all galaxies fit these tidy classifications. Some appear misshapen or irregular, likely distorted by gravitational interactions, past mergers, or ongoing encounters with neighboring systems. These irregular galaxies serve as transitional objects, snapshots of galaxies caught mid-transformation, still bearing the scars of their recent histories. In the observable universe, astronomers estimate the existence of up to 1 trillion galaxies, varying wildly in scale. Most are modest, containing a few billion stars, but a select few are true giants, hosting hundreds of billions or even trillions of stars. These galaxies are not scattered randomly. Rather, they trace a vast interconnected structure of matter known as the cosmic web, a lattice of filaments and nodes shaped by the primordial fluctuations seeded during inflation and sculpted by dark matter over cosmic time. In this web, vast voids regions nearly devoid of galaxies span millions of light years, while matter flows along filaments and sheets toward gravitational wells. These wells correspond to massive conglomerates of galaxies and dark matter. Galaxy clusters. Clusters are gravitational fortresses housing hundreds or thousands of galaxies swimming in a hot plasma called the intracluster medium, all immersed in massive dark matter halos. At the heart of the largest clusters reside the titans of the galactic realm, CD galaxies, monstrous ellipticals that dominate their environment and continue to grow through cannibalism and accretion. Clusters themselves form larger structures, superclusters which span hundreds of millions of light years. Our own Milky Way is part of one such structure, the Laniakea supercluster, encompassing millions of galaxies. Whether superclusters are gravitationally bound or merely transient associations remains an open question, but they mark the largest coherent features in the known universe. Not all galaxies live in clusters. In fact, most reside in smaller associations known as galaxy groups. These more intimate gatherings consist of a few to several dozen galaxies, typically anchored by 1 or 2 massive members. Our Milky Way is part of such a group. The local group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and over 100 dwarf galaxies. Many of these faint companions have only recently been discovered through deep sky surveys enabled by modern telescopes. The local group, while unassuming compared to massive clusters, has become a laboratory for understanding galactic evolution. In particular, it has revealed a truth that reshapes our conception of galaxies as static finished entities. Galaxy evolution is not over. In fact, it is happening around us right now. A striking example of this ongoing process was discovered in the early 1990s by Rodrigo Ibada, a young graduate student at the University of Cambridge, working with the Anglo-Australian Telescope in New South Wales. Ibada was studying the dynamics of stars near the Milky Way's central bulge. His observations, conducted with the aid of optical fiber instruments capable of measuring the motion of dozens of stars, simultaneously uncovered something strange. Amid the random motions expected in the galactic bulge, a subset of stars appeared to be moving coherently, as if they shared a common origin. Ibata ruled out measurement errors and computational mistakes. The evidence grew harder to ignore. With the guidance of his supervisors, Jerry Gilmore and Mike Irwin, Ibata reached a bold conclusion. These stars were not native to the Milky Way. They belonged to a separate external system, an intruding dwarf galaxy. The discovery of the Sagittarius dwarf galaxy provided direct evidence that the Milky Way was in the process of consuming another galaxy. This satellite galaxy, stretched and distorted by our galaxy's gravity, was being torn apart, its stars scattered into tidal streams across the sky. What was once a coherent stellar system would eventually be subsumed into the Milky Way's halo, lost among its billions of stars. Since then, astronomers have found that Sagittarius is not alone. The Milky Way is consuming multiple dwarf galaxies, remnants of which are still detectable in the form of faint stellar streams. Andromeda, our galactic neighbor, is doing the same. Galactic cannibalism is not an occasional event. It is a central mechanism of galactic growth. The peaceful serenity we attribute to our night sky belies a violent and ongoing process of accretion and destruction. Thus, our understanding of the galactic zoo, the diversity of galaxies and their behaviors, has matured through decades of observation and theoretical work. We now comprehend galaxies not as isolated objects, but as products of environment history and ongoing interaction. They are born in the dense knots of dark matter, nurtured by gravity and gas, shaped by internal dynamics and transformed by cosmic encounters. They live, grow, and sometimes die, collapsing into black holes or being devoured by larger systems. Yet for all our knowledge, the universe continues to challenge us. As recently as 2022, new observations from the James Webb Space Telescope hinted that the earliest galaxies might be more massive and more developed than current models predict, stirring debates and forcing us to re-examine long-held assumptions. From the quantum ripples that ceded structure to the majestic spirals and monstrous clusters we observe today, the cosmos reveals itself as both an archive of ancient processes and an active dynamic entity. To map this evolution is to trace a vast and interwoven story, a narrative written in stars and dark matter and gas and radiation in the grand interplay of gravity and time. It is the story of everything we see in the night sky, and it is still being written. The James Webb Mystery. It began with a roar that echoed across the blue Christmas morning sky, a column of fire lifting humankind's most ambitious eye into the heavens. A telescope unlike any before. It folded like cosmic origami, was flung across the void to take position 1.5 million kilometers from Earth, far beyond the pull of our planet's gravity, to a place where the forces of Earth and Sun are balanced in celestial harmony. There, at the second Lagrange point, JWST unfurled its golden mirrors, cooled to the chill of deep space, and prepared to look far back toward the first flickers of starlight that ever pierced the darkness. As the James Webb Space Telescope opened its eye on the young universe, astronomers around the globe found themselves transfixed and then puzzled. What they saw in those first images from the primordial cosmos did not align with what decades of theory had led them to expect. There, shining from a time less than 1 billion years after the Big Bang, were galaxies that looked too big, too luminous, too structured. Some were beautiful, rotating disks, grand spirals eerily reminiscent of our own, Milky Way. But how could this be? In a universe still in its infancy, how had such galaxies already matured? One paper, cheekily titled "Panic at the Disks," captured the sentiment cosmologists watched as headlines around the world began to declare an existential crisis had JWST disproven the very foundations of cosmology. Was the Big Bang model broken? Were the equations of the universe undone? To make sense of the excitement and the unease, we must journey into the very heart of modern cosmology and ask a simple but profound question: what kind of universe do we live in? The story begins, as so many great stories do, in the early 20th century. Albert Einstein, forging a new understanding of gravity, had just unveiled his general theory of relativity, a framework in which space and time were no longer passive stages, but active participants in the cosmic dance. Others followed in Einstein's wake: Friedman, Lemaitre, Robertson, Walker. Their solutions to Einstein's equations revealed a startling possibility: space itself was not static. The universe could stretch, evolve, and expand. And then came Edwin Hubble. In the 1920s, observing from Mount Wilson, he found that distant galaxies were redshifted. That is, their light was stretched as if fleeing from us. The more distant the galaxy, the greater the shift. The conclusion was inescapable. The universe was expanding. And if it was expanding now, it must have been smaller, denser, and hotter in the past. Thus was born the Big Bang theory, not an explosion in space, but an expansion of space itself from a seething, high-energy beginning. But relativity, elegant as it is, offers not one solution, but many. Mathematically, the equations can describe countless possible universes. To know which one we inhabit, astronomers needed data, specifically 2 crucial measurements: the current rate of expansion and the contents of the universe. The first of these is the Hubble constant, which tells us how fast galaxies recede as a function of their distance. The second concerns the energy budget of the cosmos, how much of it is made of matter, radiation, and other more exotic components. Measuring these values became the central task of observational cosmology for most of the 20th century. Determining the Hubble constant was notoriously difficult. The universe, unfortunately, does not provide measuring sticks. Estimating cosmic distances required creative methods using standard candles like Cepheid variables and Type Ia supernovae, whose intrinsic brightness is known to deduce their distance from apparent brightness. For decades, astronomers debated whether the Hubble constant was closer to 50 or 100 kilometers per second per megaparsec, a disagreement that translated into wildly different estimates of the universe's age. It was only in the 1990s, with the deployment of the Hubble Space Telescope, that clarity began to emerge. With unprecedented precision, HST measured the distance to nearby galaxies, settling on a value near 72 kilometers per second per megaparsec, implying a universe roughly 138 billion years old. Visible matter stars, planets' gas was easy enough to tally, but something strange lurked in the motions of galaxies and clusters. Spiral galaxies rotated too fast at their edges. Clusters of galaxies held together despite insufficient visible mass. The only explanation was that some unseen substance, dark matter, was exerting gravitational influence. Though invisible to light, its presence was undeniable. The universe, it seemed, was mostly made of things we could not see. And then came a revelation so startling, it won the Nobel Prize 2 teams. The Supernova Cosmology Project and the High-Z Supernova Search Team studied the light of exploding stars to chart the expansion history of the universe. Their expectation was clear: Gravity, acting over time, should slow the expansion. But the data told a different story. Instead of decelerating, the universe was accelerating, expanding faster and faster as time went on. What could be driving this cosmic acceleration? The answer, though speculative, lay in the mathematics of general relativity, a mysterious form of energy permeating all of space, exerting a repulsive pressure. It became known as dark energy, a force unlike any seen before, whose nature remains one of the deepest mysteries in physics. With these discoveries, cosmologists assembled a model of the universe now known as LCDM, lambda, cold, dark matter. Lambda stands for the cosmological constant, Einstein's term for dark energy. CDM refers to cold dark matter, slow-moving and clumping, which seeds the formation of galaxies. According to LCDM, the universe is 138 billion years old, composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. This model has passed countless observational tests. It predicts the pattern of cosmic microwave background radiation, the distribution of galaxies on large scales, and the evolution of cosmic structure. It is by all accounts an astounding triumph of science. The galaxies observed by JWST appeared not only earlier than expected, but brighter, more massive, and more structured than models had predicted. Some appeared to contain hundreds of billions of stars, less than a billion years after the Big Bang. In theory, such massive systems shouldn't have had enough time to form. Cosmological models like LCDM govern the evolution of the universe on the largest scales, how space expands, how matter clumps. But to predict the formation of galaxies, we must go further. We must simulate the flows of dark matter and gas, the cooling of plasma, the birth of stars, the feedback of supernovae and the ravenous hunger of black holes. This is astrophysics in full complexity, a dance of scales and forces that challenge even our most powerful computers. To cope, astronomers employ recipes, simplified rules embedded in simulations to approximate the messy physics of galaxy formation. These recipes are based on the best available data but often rely on assumptions. One of the most critical is the stellar initial mass function, a statistical description of the distribution of star masses formed in a given gas cloud. In the local universe, the IMF is relatively well constrained. But what if it was different in the early cosmos? If, for example, early star formation favored more massive luminous stars, then young galaxies would shine more brightly than expected, for their mass astronomers, assuming a local IMF, would overestimate their size and maturity. Such a skewed IMF could help explain why JWST's galaxies seemed anomalously bright. Perhaps they weren't so massive after all, just composed of hotter, more massive stars. Moreover, early results from JWST were based on rapid preliminary analyses. The telescope's instruments are extraordinarily sensitive, and interpreting their data requires meticulous calibration. Redshifts must be confirmed spectroscopically, not just estimated photometrically. Initial excitement often gives way to more sober reanalysis. And that is precisely what is happening. As JWST continues its observations and astronomers refine their models, the panic is subsiding. The LCDM framework remains intact. The early universe may be more complicated than expected, richer, more dynamic, but that is not a crisis. It is the fulfillment of JWST's mission. For telescopes do not exist to confirm what we already know. They are built to challenge our assumptions, to expand the boundaries of the known. Every deviation, every outlier, every unexpected galaxy is a clue, an invitation to look again, think deeper, and refine our understanding of the cosmos. What the James Webb Space Telescope is revealing is not the failure of cosmology, but its vitality. It reminds us that science is not a monument, but a process, a conversation with nature that unfolds over time. It is a testament to our curiosity, our creativity, and our willingness to question even our most cherished theories. In the end, the galaxies JWST glimpsed in the early cosmos are not harbingers of doom, but messengers of wonder. They whisper of a universe that came alive faster than we imagined, of stars that blazed into existence amid chaos, and of a cosmos still full of secrets waiting to be unveiled. And so the story continues, one observation at a time, one photon at a time, as we reach deeper into the darkness, searching not for certainty, but for understanding. And of a cosmos still full of secrets waiting.
What if the entire universe was built from invisible bricks, smaller than anything we could ever see? What if every star, every planet, even you and I, were made from the same fundamental pieces? And what if, at the dawn of time, not a single one of them existed? The ship hums softly as it pierces the void, its frame trembling with anticipation. A crew, tense but determined, embarks on a voyage not across solar systems or galaxies, but into a realm far stranger. They are not astronauts, but atomonauts, explorers venturing into the heart of matter itself. Their mission: to traverse the inner architecture of the simplest atom in the universe, hydrogen. Departing from its solitary proton, they set out in search of the elusive electron that dances invisibly in the space around it. Unlike the moon-bound journeys of Apollo, which spanned mere tens of Earth diameters, this expedition covers a space unimaginably vast in relative scale, more than 63,000 times the width of their homeworld. But size is not the only strangeness. This isn't an orbit as Newton imagined, nor a path we can trace with certainty. In the quantum realm, the electron does not follow a neat trajectory. It exists in a haze of probability, a shimmering cloud of possibilities. To land is impossible, to locate is uncertain, and yet everything in the known universe is built from such mysteries. These atoms, tiny, unknowable, yet persistent, are the cosmic Lego bricks from which all structure arises. Stars, oceans, minds, and memories, all woven from these quantum whispers. And yet, at the very beginning, there were none. Not one atom stirred in the newborn cosmos. So where did they come from? How did something so fundamental emerge from a universe that began with nothing? Let us begin the smallest place imaginable to answer the biggest questions we've ever asked. The first light in the universe. Where did the first light come from? And what does it reveal about the birth of atoms, the fabric of our cosmos, and the nature of existence itself? A storm churns across the Black Sea. The tranquil surface, once a polished mirror to the sky, becomes a chaos of wind and wave. In the midst of this watery turmoil drifts a fragile kayak, barely more than a silhouette against the gray tumult. Inside it are two figures, a young physicist and his new bride. They are fugitives, not from war, but from an intellectual prison, fleeing a state increasingly hostile to curiosity, reason, and the pursuit of truth. The year is 1932. The physicist is George Gamow, born in Odessa, already known among European scientists for his brilliant theoretical insights. With him is Lyubov Volkmantseva, whom he affectionately calls Ro, after the Greek letter. Their union, both romantic and intellectual, is born under duress. In the Soviet Union, the winds have turned against scientists, with foreign ties or unconventional ideas. Travel abroad is tightly controlled. Gamow, eager to present his latest research at a conference in Rome, finds himself repeatedly stalled by Soviet bureaucracy. The passport office in Leningrad offers him no escape, only delay. But in that very same office, amid endless queues and shattered hopes, he meets Ro. They fall in love. They marry. And soon after, they make a bold and desperate decision to flee across the Black Sea and seek asylum in the West. Their plan is as daring as it is unlikely. They aim to reach Turkey by sea, navigating under cover of darkness, with only an old kayak and Gamov's Danish motorcycle license, acquired during his time with Niels Bohr in Copenhagen, as their hope for a plausible identity. The goal is simple: land on a Turkish beach, claim to be Danish, and plead for help from the Danish embassy in Istanbul. At first, nature is on their side. Calm waters, light winds. But by the second morning, the sea turns savage. A violent storm rises, and their fragile vessel is no match. Exhausted, delirious, they are cast adrift and blown back toward Crimea. Their escape seems doomed, but eventually, with persistence and luck, they succeed. By 1934, they have left the Soviet Union behind for good, arriving in the United States, where Gamov would spend the rest of his life. And yet, the ideas born in his mind and the collaborations he would foster would help reshape our understanding of the entire universe. In the late 1920s, science was undergoing a revolution. Just 3 years before Gamov's escape, American astronomer Edwin Hubble had published findings that shook the foundations of astronomy. Galaxies, those distant glowing spirals, were not stationary. They were moving away from us, and not slowly. The further away they were, the faster they receded. If space itself was stretching, then it followed logically that the universe must have once been much smaller. Wind back time far enough, and every star, every planet, every atom must have been compressed into a single, unimaginably dense point. The idea would come to be known as the Big Bang, but in truth, it was not new to Gamov. Nearly a decade earlier, back in Leningrad, he had studied the equations of Alexander Friedmann, the Russian physicist who first derived a model of an expanding universe from Einstein's general relativity in 1925. The seeds of the Big Bang had been planted long before Hubble's observations. When Gamow arrived in America, his primary research interest was not cosmology, but the processes that power stars. Specifically, he was fascinated by nuclear fusion, the transformation of lighter atomic nuclei into heavier ones under immense pressure and temperature, releasing energy in the process. He understood that the same conditions that fuel the stars must once have existed throughout the entire cosmos long ago. In 1945, shortly after the end of World War II, Gamow began to connect the dots. He wrote to his old mentor, Niels Bohr, noting his growing interest in applying stellar physics to the conditions of the early universe. What if the entire cosmos, in its infancy, had once resembled the core of a star? Together with his student Ralph Alpher, Gamow developed a bold hypothesis that the early universe was hot, dense, and filled not with matter, but with radiation, specifically electromagnetic radiation. In their 1948 paper, often humorously referred to as the Alpha Beta Gamma paper, they proposed that shortly after the Big Bang, the universe was dominated not by atoms, but by light itself. This radiation, what physicists call electromagnetic energy, was not the kind of light our eyes are sensitive to. It spanned a vast spectrum, from high-frequency gamma rays to low-frequency microwaves. Just as there are sounds beyond the range of human hearing, so too there are wavelengths of light beyond our sight. But even though invisible to our eyes, this light held the power to shape matter. In the early universe, matter and light were inseparably intertwined. Photons, the particles of light, were trapped in a sea of charged particles, protons, electrons, and nuclei. The universe was opaque, like the interior of a star. Light could not travel freely. It bounced endlessly off charged particles in a chaotic dance. This era is sometimes called the photon epoch. It lasted for tens of thousands of years. During this time, matter was still forming, but radiation ruled. As the universe expanded, it cooled. Lower temperatures allowed protons and electrons to combine and form neutral hydrogen atoms, a process known as recombination. This is somewhat of a misnomer, as it was the first time these particles had ever combined in the universe. But the terminology stuck. With electrons now bound to protons, the universe became transparent for the first time. Photons were no longer scattered by free charges. They could finally move unimpeded, traveling vast distances without interruption. This release of photons, this first escape of light, is what we call the cosmic microwave background. Though we now detect it as faint microwave radiation, this light is a snapshot of the universe in its infancy, a moment frozen in time. It holds the patterns of tiny temperature fluctuations, the seeds of galaxies and cosmic structures that would form billions of years later. It is, quite literally, the first light of the cosmos. They also investigated what the early universe might have synthesized. Could all the elements we see today, carbon, oxygen, iron, have formed in that primordial fireball? Their conclusion was that only the lightest elements, hydrogen and helium, and trace amounts of lithium could have formed during the Big Bang. Heavier elements, they argued, must have been forged later, in the hearts of stars. This idea, now known as Big Bang nucleosynthesis, remains a pillar of modern cosmology. In those early dense epochs, the universe was dense enough for pressure waves, compressions, and rarefactions to ripple through it. These primordial sound waves, now stretched by billions of years of cosmic expansion, left their imprint on the large-scale structure of the universe. We call these patterns baryon acoustic oscillations. Though inaudible now, far below the threshold of human hearing, these waves can be detected through sophisticated surveys like the Sloan Digital Sky Survey. In a poetic gesture, physicist John G. Kramer even converted these ancient oscillations into audible sound using data from the early universe. The result? A deep, eerie rumble, a cosmic echo from the dawn of time. And so from a stormy kayak voyage across the Black Sea to the luminous echoes of the Big Bang, we follow a thread of human curiosity that stretches across oceans, decades, and cosmic epochs. Gamov's life was emblematic of the power of science to transcend borders, political, geographical, and even temporal. His ideas helped illuminate the very origins of matter and light. The radiation that first poured across the newborn universe now bathes us from every direction, whispering the history of everything that has ever been. All of it, every star, every atom, every breath you take, can be traced back to those first few 100,000 years, to that light, to those waves, to the moment when the fog lifted and the universe opened its eyes. And all of it began with a question, not just where did everything come from, but how did the first light begin to shine? The weirdest object in the universe. Imagine yourself lost in a maze so dense, so impenetrable that every step forward ends in a wall. Turn left, dead end. Turn right, another. No landmarks, no pattern, no exit. Claustrophobia builds not from darkness, but from the realization that space itself offers no release. This was the condition of light in the earliest moments of the universe. In the seconds following the Big Bang, light was not the liberating, illuminating phenomenon we know. It was a prisoner of its own making, ensnared in a trap forged by its deep relationship with matter. Wherever photons tried to travel, they collided with a relentless soup of subatomic particles, bouncing, scattering, imprisoned. But to understand why light was caged, we must first understand what light is, Light, for all its elegance, is energy incarnate, a vibration in the fabric of the electromagnetic field. And energy, as Einstein taught us, is interchangeable with mass. In the high-energy furnace of the infant universe, light did what it could rarely do today. It shapeshifted into matter. Just fractions of a second after the universe was born, the searing temperatures reached over a quadrillion degrees. In these conditions, the energy of photons was so immense that light spontaneously transformed into particles, electrons, quarks, neutrinos, and their antimatter twins. Matter began to dominate the universe, but not yet in the form we recognize. At this stage, it was wild, chaotic, and unbound. To build atoms, those structured, composed units that underpin the universe, we needed more than just electrons. We needed protons, and for that, we needed something even more elementary: quarks. Quarks come in 6 varieties or flavors: up, down, charm, strange, top, and bottom. But only 2 are needed for the architecture of ordinary matter: up and down quarks. A proton is composed of 2 up quarks and 1 down quark, while a neutron is made of 1 up quark and 2 down quarks. These combinations sound simple, but the forces binding them are anything but. Quarks possess electric charge. Up quarks are positively charged, and down quarks are negatively charged. So how do 2 positive charges sit together within a proton without flying apart? The answer lies in one of the 4 fundamental forces of nature, the strong nuclear force. While gravity governs planets and stars, and electromagnetism dictates the behavior of light and charge, the strong nuclear force is the mighty glue that holds the nucleus of every atom together. It is, by every measure, the most powerful force known, 10 to the power of 38 times stronger than gravity. Yet this immense power comes with a caveat. It acts over vanishingly small distances, less than a trillionth of a millimeter. In the scorching, turbulent early universe, where particles zipped around with almost unimaginable kinetic energy, even this strong force was overwhelmed. Quarks could not bind into stable triplets like protons and neutrons. Not yet. Only when the universe had expanded and cooled for a millionth of a second did temperatures fall to about 1 trillion degrees. Then, and only then, could quarks be tamed into nucleons. The first protons and neutrons formed, stable, robust, and ready for the next stage in matter's long journey toward atoms. And yet, the story of the proton, far from being one of simplicity, is among the strangest in physics. Ask a physicist where a proton is, and they may smile ruefully. It's complicated, they'll say, because despite decades of investigation, the proton remains one of the most bizarre, elusive, and intricate objects in the universe. For one thing, the 3 valence quarks that compose the proton account for only 1% of its mass. The other 99% comes not from stuff in the traditional sense, but from a swirling storm of virtual particles and force carriers. Chief among them, the gluon. Gluons are the messengers of the strong nuclear force. They dart between quarks, binding them through a dance of continuous exchange. But unlike the photon, which carries the electromagnetic force without interacting with other photons, gluons interact with each other. This creates a tangled web of field interactions, spawning a sea of virtual particles. These sea quarks and their antiparticles briefly blink into existence within the proton. They borrow energy from the vacuum, just enough, just briefly enough, to satisfy quantum uncertainty. They annihilate and reform in a frenetic blur. The result is a particle that is more cloud than core, a restless, stormy sea of fluctuating mass and energy. In truth, the proton is less an object than a process, a bubbling, dynamic storm of quantum activity. Experiments like those at the relativistic heavy ion collider, RHIC in New York, have confirmed that the proton's mass is emergent. It arises not from the mass of its constituents, but from the energy of their interactions. Even stranger, these virtual C quarks can include heavier varieties, like charm quarks, that are far more massive than the proton itself. A single charm quark has about 1.5 times the mass of the entire proton, yet they appear, briefly, without breaking the laws of conservation. This quantum weirdness, particles popping in and out of existence like flickering ghosts, doesn't just influence the proton, it defines it. Now that protons and neutrons exist, the universe's expansion continues. Particles slow, space cools, and a crucial window opens. Roughly 1 second after the Big Bang, the cosmos reaches a temperature of around 10 billion degrees. This is cool enough for protons and neutrons to begin binding together, held by the strong force, into simple nuclei. The first of these is the deuteron, composed of 1 proton and 1 neutron. It is the precursor to all heavier atomic nuclei. Enter George Gamow and his collaborator Ralph Alpher. In 1948, they published a groundbreaking paper, brief but revolutionary, in which they outlined the series of nuclear reactions that transformed the early universe's hydrogen into helium. This process, called Big Bang nucleosynthesis, took place within a 20-minute window. During this time, the conditions were just right for nuclear fusion to operate across the entire cosmos, just as it would billions of years later in the cores of stars. Through a rapid series of reactions, deuterons fused with additional protons and neutrons, creating helium-3, helium-4, and a trace of lithium. By the end of this short epoch, about 25% of the universe's mass was in helium nuclei. The remaining majority was hydrogen. But this was not yet the formation of atoms. What was created in the first 20 minutes were nuclei, the dense, positively charged cores of atoms. To complete the picture, they needed electrons. Electrons, lighter and more elusive than protons, had been present since the very beginning, but they roamed freely, constantly interacting with photons and other charged particles. Their journey into bound orbits required a universe that had cooled significantly more. The electromagnetic force, the one responsible for attracting negatively charged electrons to positively charged nuclei, is much weaker than the strong force. To give it a chance to bind electrons into orbits, the universe needed to cool to just 4,000 degrees Kelvin. That would take time. It was only then, in this cooler and more expanded cosmos, that electrons could finally settle into orbitals around nuclei, forming neutral atoms. This moment is called recombination, though in truth it was the first combination. With electrons now bound, photons were freed from constant scattering. Light, for the first time, could travel unimpeded. This release of photons is what we now observe as the cosmic microwave background, the afterglow of the Big Bang, stretched into microwaves by billions of years of cosmic expansion. It is the oldest light in the universe, a relic from a time when the first atoms were born. But even these electrons, the humble negative companions to protons, harbor strangeness. Electrons, as far as we can tell, are point particles. They have no internal structure, no spatial extent. They are, in the language of physics, truly fundamental, and yet they defy simple description. Electrons do not orbit nuclei in neat planetary tracks. Quantum mechanics tells us that such imagery is misleading. Instead, electrons exist as probability clouds, their positions uncertain, their velocities unknowable with precision. The Heisenberg uncertainty principle ensures that the best we can do is calculate the likelihood of finding an electron in a certain region. Moreover, electrons possess spin, a quantum property that defies classical analogy. Though we often describe it as rotation, this is a metaphor. Electrons do not spin in space. Yet their spin governs magnetic interactions and determines how electrons fill atomic orbitals, giving rise to the periodic table and the structure of matter. Spin half particles like electrons also exhibit another counterintuitive behavior. They must rotate 720 degrees, not 360, to return to their original quantum state. This bizarre fact lies at the heart of quantum field theory and hints at the deep symmetries that underlie our universe. Thus, within every atom, within every breath of air, every drop of water, every star and cell and stone, is a swirling, probabilistic hall of mirrors, quarks that blink in and out of existence, gluons that bind the impossible, electrons that refuse to be pinned down. What seems so tangible and solid is built atop a bedrock of uncertainty and abstraction. And yet from this chaos, order emerges. Atoms became the building blocks of molecules, molecules the scaffolding for chemistry, chemistry the stage for biology. The structure of the universe, galaxies, stars, planets, people, flows from the first moment when light was set free by the formation of neutral atoms. In 1948, Ralph Alpher and Robert Herman predicted that the glow from that moment of release, the relic radiation of recombination, should still be visible. It would have cooled by now, they reasoned, stretched into microwaves. But their insight, profound as it was, went largely unnoticed for decades, until two radio astronomers working on a different problem in Holmdel, New Jersey, stumbled across a hiss that came from every corner of the sky. They had found the ghost of recombination, the first light, the proof that the universe began hot, dense, and full of potential. That light is still with us, whispering across the eons. It is the silent testimony of a time when the weirdest object in the universe, the atom, was first forged from light and fire. Seeing the Big Bang, a tale of invention, serendipity, and the echoes of creation. On a crisp September morning in 1941, a young Robert Dix stood atop the radiation laboratory at the Massachusetts Institute of Technology, cradling a device of his own design. At just 25 years old, fresh from completing his PhD, Dick was already making waves. Yet few could foresee how his curiosity, first sparked by war, then stoked by wonder, would help reveal the earliest light in the universe. Dick's arrival at MIT coincided with one of the most pivotal moments in modern history. The world was already 2 years into the Second World War, and while the United States had not yet joined the fight, preparations were underway. Within weeks of his arrival, Japan bombed Pearl Harbor, and the U.S. entered the conflict the very next day. This marked the beginning of Dick's career in wartime science, a crucible of innovation that would leave lasting imprints on both technology and cosmology. At MIT, Dick's task was urgent and critical: radar development. The term radar had only recently been coined by the U.S. Navy. The principle was simple yet powerful: emit bursts of radio waves and detect their echoes off distant objects, such as enemy aircraft. However, early radar systems were crude. Their long radio wavelengths meant the details they captured were limited, much like trying to perceive fine brushstrokes through frosted glass. Dicke, with his keen engineering instincts and flair for invention, turned his attention to microwaves. Unlike radio waves, microwaves have much shorter wavelengths. The advantage was clear: finer resolution and greater sensitivity. This led to one of Dicke's key wartime inventions, the Dicke radiometer, a device finely tuned to detect faint microwave signals with unprecedented precision. Yet for all his contributions to military technology, Dicke's mind often wandered skyward, beyond the threats of bombers and missiles. He began to wonder, were there signals, not of war, but of nature, coming from space? Were there whispers of ancient cosmic events hidden in the microwave part of the electromagnetic spectrum? This thought stayed with him, quietly simmering for over a decade. After the war, Dicke returned to academia, joining the faculty at Princeton University. There, he rekindled his interest in the cosmos and began to seriously consider one of the most profound questions in all of science: How did the universe begin? At the time, the Big Bang theory was gaining traction, but it was far from universally accepted. The idea that the universe originated from an unimaginably hot, dense state and had been expanding ever since was as philosophically jarring as it was scientifically compelling. How does something come from nothing? Was and remains a natural reaction to the theory. Dicke, never satisfied with easy answers, explored alternatives. He considered a cyclical universe, one that expands, slows, reverses, and collapses in a grand Big Crunch, only to explode once more in a renewed Big Bang. An eternal cosmic heartbeat. Within this framework, Dicke envisioned a dramatic phase in the universe's history. As the cosmos contracted, temperatures would skyrocket, reducing matter to a primordial soup of protons, electrons, and subatomic debris. This incandescence, a searing fireball of radiation and particles, would be the crucible from which the universe would be reborn. During the subsequent expansion, the fireball would cool, and conditions would again become favorable for atoms to form. This process, he reasoned, could leave behind a telltale sign: residual radiation from that fiery epoch, lingering like a ghost in the cosmos. Unbeknownst to Dicke at first, this idea was not entirely novel. As early as 1948, physicist George Gamow and his collaborators Ralph Alpher and Robert Herman had predicted just such a relic. They hypothesized that if the early universe had been hot and dense, it would have emitted thermal radiation, initially visible light, that would persist even today, albeit stretched by cosmic expansion into the microwave part of the spectrum. Dicke independently arrived at the same conclusion. Building on his deep knowledge of microwave detection, he proposed searching for this fireball radiation, a fossil echo of the universe's formative moments. He surmised that over the billions of years since its emission, this radiation would have been redshifted by the expansion of space, moving it from the visible into the microwave region. If it existed, it should still be detectable using the kind of instrumentation he had been refining for decades. He began preparing for the observation campaign in the early 1960s, assembling a team and designing equipment. But fate intervened. Just 45 miles away, in Holmdel, New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were working on a very different problem. They weren't hunting cosmic relics. Instead, they were trying to eliminate noise from their measurements of satellite signals, using the massive 6-meter Holmdel horn antenna at Bell Labs. The noise they encountered was persistent and puzzling, a steady isotropic hiss that refused to go away. They were meticulous in their troubleshooting. Local sources of interference were ruled out. They cooled their receiver to near absolute zero using liquid helium, eliminating thermal noise. Still, the signal remained. Eventually, they discovered a pair of pigeons had taken up residence in the antenna, leaving behind what they later described as white dielectric material. The pigeons were gently removed and relocated, only to return. Eventually, with regret, they were euthanized. The antenna was cleaned, but the hiss endured. The signal, it seemed, was coming from every direction in the sky. Confounded, Penzias reached out to colleagues for insight. One of those calls went to Robert Dicke. At that very moment, Dicke and his team were in the middle of planning their own search for the fireball radiation. When he heard what Penzias described, Dicke turned to his colleagues and said, simply, "Well, boys, we've been scooped." Penzias and Wilson had unwittingly detected the cosmic microwave background, the faint afterglow of the Big Bang, the exact signature Dicke had set out to find. Their serendipitous discovery, published alongside a companion theoretical paper from Dicke's group, confirmed one of the most profound predictions of modern cosmology. In 1978, Penzias and Wilson received the Nobel Prize in Physics. Dick, Gamow, Alpher, and Herman would never claim that honor. Yet their contributions laid the foundation for what is now one of the cornerstones of cosmological science. The CMB is more than just a technical curiosity. It is a snapshot of the universe when it was just 380,000 years old, a newborn in cosmic terms. At that time, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. That light, now stretched into microwaves, fills the universe. If the universe were a 40-year-old human, the CMB is the equivalent of a photo taken in the first 10 hours of life, a baby picture of everything. Yet this image is not smooth. Embedded in the CMB are minute temperature fluctuations, tiny differences in density, that seeded the large-scale structure of the cosmos. Where there was slightly more matter, gravity pulled in more, amplifying the contrast. Over time, these regions became the galaxies, clusters, and filaments we observe today. These fluctuations also preserve the echoes of sound waves, pressure oscillations in the hot plasma of the early universe, known as baryon acoustic oscillations. Like ripples frozen in time, they mark the rhythmic pulse of the infant cosmos. Today, surveys such as the Dark Energy Survey in the Chilean Andes map the universe in stunning detail. They reveal a vast, web-like structure, superclusters of galaxies and immense voids, all tracing the patterns etched into the CMB nearly 14 billion years ago. The seeds of the present were sown in the earliest moments, and remarkably, you don't need a giant telescope to sense this ancient light. In the era before digital broadcasting, an old analog television set could detect it, tune between channels, and a portion of the static, the snow dancing across the screen, was the cosmic microwave background whispering across time. This signal will outlast us. It will fade only after trillions of years of continued expansion, eventually stretched beyond detection. But for now, it remains a testament to a moment when atoms first formed, when the universe became transparent, and when the light of creation began its journey to us. It's tempting to think that atoms were an inevitable outcome, that in any universe filled with light and matter, they would naturally form. But this is far from certain. The conditions had to be just right. A slightly different rate of expansion, a different balance of forces, and atoms might never have formed. No stars, no galaxies, no life. The formation of the first atom wasn't a guarantee. It was a cosmic triumph, and the light from that triumph still surrounds us. Woven into the very fabric of space, it is the echo of a fireball that once lit up the universe and has never truly gone dark. Why atoms? Imagine, for a moment, standing blindfolded before 24 loaded rifles, their barrels aimed squarely at your chest. You hear the subtle metallic clicks as the triggers are drawn back. Feel the tension of your final breath and brace for oblivion. Then, miraculously, every single shot misses. Not one, not two, but all 24 projectiles fail to find their mark. You survive. This dramatic thought experiment, proposed by Canadian philosopher John Leslie in his 1989 book, Universes, serves as a powerful metaphor for the seemingly improbable circumstances that allow our universe to exist, and more specifically, to allow atoms to exist at all. Just as it only takes one bullet to end a life, it would take only a minuscule tweak in the laws of physics to snuff out the existence of atoms. Yet here we are, awash in a cosmos teeming with them. From the moment of its birth, 13.8 billion years ago, the universe has undergone an extraordinary transformation. It began as an almost unfathomably hot, dense, and chaotic state, devoid of any structure. Today, it contains more atoms than we could hope to count in trillions upon trillions of lifetimes. Atoms form the scaffolding of all matter, from the most distant galaxies to the neurons in your brain. We take them for granted, but their very existence is predicated upon a precise balance of cosmic parameters, each one tuned so delicately that even the slightest adjustment would obliterate this fragile architecture. Let us consider a metaphorical control panel covered with dials, sliders, and switches, each governing a fundamental property of the universe: the masses of subatomic particles, the strength of fundamental forces, the rate of cosmic expansion. Tinker even slightly with the settings on this cosmic console, and atoms, the bedrock of chemistry and biology, would unravel. One of the most crucial parameters is the ratio between the size of electron orbits and the size of the atomic nucleus. For an atom to be stable, electrons must orbit at distances far greater than the size of the nucleus. If the electromagnetic force were even slightly stronger, electrons would spiral inward, crashing into the nucleus like satellites burning up on atmospheric re-entry. If the force were weaker, electrons would escape altogether, leaving protons isolated and chemistry impossible. But it's not just electromagnetism. The strong nuclear force, which binds protons and neutrons within the nucleus, must also be precisely tuned. Weaken it by just a small fraction, about 9%, and it would be too feeble to hold protons and neutrons together in the simplest nucleus, the deuteron. No deuterons, no fusion in the early universe. Strengthen it by just 2%, and 2 protons could bind into a diproton, a particle never observed in nature. Such particles would have rapidly fused into helium during the Big Bang, depleting the universe's supply of hydrogen, the foundational element upon which stars and life depend. The degree of fine-tuning required is staggering. A physicist would say these forces are finely tuned, a term that belies the almost cosmic improbability of the settings being just right. This idea, now central to debates in cosmology and philosophy, was first articulated in a meaningful way by physicist Robert Dicke in 1961. He argued that the universe appears biophilic. Its parameters fall into a narrow range that permits life. But it isn't only the fundamental forces that are delicately arranged. Consider the masses of the particles themselves. The neutron is just slightly heavier than the proton, by about 1/7 of 1%. This small disparity is critical. Were the neutron lighter, it wouldn't decay, and the balance of matter in the universe would be entirely different. If it were much heavier, it wouldn't form stable nuclei at all. If the electron were heavier than the mass difference between proton and neutron, it could be captured by protons, transforming them into neutrons and disrupting atomic structure altogether. These masses depend in turn on the quarks that make up protons and neutrons. A proton is composed of 2 up quarks and 1 down quark, while a neutron contains 2 downs and 1 up. The down quark is slightly more massive than the up quark, a difference that tips the scales just enough to make the neutron heavier. Were this mass difference altered even slightly, the entire narrative of the universe would change. Neutrons could decay into protons in an uncontrolled manner. Deuterons would become unstable, and the formation of elements beyond hydrogen would be thwarted. No oxygen, no carbon, no periodic table. And yet, through a delicate interweaving of forces and particles, atoms came into being. Their progenitors, the quarks, gluons, electrons, emerged within microseconds of the Big Bang. Within minutes, protons and neutrons fused into simple nuclei. Hundreds of thousands of years later, these nuclei captured electrons to form neutral atoms. Stars lit up, forged heavier elements, and exploded them into space, seeding the cosmos with the raw ingredients for planets, oceans, and life. Such a tale naturally invites questions. Why is the universe so precisely arranged? Why does it permit atoms at all? Why do we find ourselves in a cosmos capable of not only building complex structures, but also of reflecting on its own origins? To explain this fine-tuning, scientists and philosophers have proposed three broad possibilities. The first is sheer chance. Perhaps we simply won the cosmic lottery. The parameters had to take some values, and by astronomical coincidence, they fell into the narrow range that permits atoms. This explanation is logically consistent, but emotionally unsatisfying to many. The odds of getting all the settings right are comparable to selecting a single star, the Sun, out of a bag containing every star in the observable universe. Possible? Yes. Likely? Hardly. The second possibility posits design. Perhaps some conscious agent, be it a deity or an advanced civilization, deliberately tuned the settings. The universe, in this view, is a kind of simulation, a grand design meant to host life. While this idea has intuitive appeal, especially in the wake of our own increasing prowess with simulations and artificial intelligence, it steps beyond the empirical into the metaphysical. The third explanation, and perhaps the most scientifically adventurous, is the multiverse. In this framework, our universe is but one of countless others, each with its own set of physical laws. These alternate universes could arise from different quantum fluctuations in a grand cosmic landscape, as suggested by theories like eternal inflation or string theory. In this view, all possible values of the dials are realized somewhere. Most of these universes are sterile, no atoms, no stars, no life. But a few, like ours, happen to have the right settings. And naturally, we find ourselves in one of those rare few where atoms exist, because only such a universe can produce observers to contemplate it. This line of reasoning is a form of the anthropic principle. It doesn't explain why the universe is finely tuned. It merely reframes the question. Out of all the possible cosmic realities, we could only ever exist in one that permits our existence. The idea of the multiverse remains speculative, but it's not without support. Observations of the cosmic microwave background, the afterglow of the Big Bang, suggest that inflation, a rapid expansion of the early universe, did occur. And in many versions of inflation, it never ends completely, giving rise to a branching tree of universes, each with different properties. Regardless of which explanation is correct, chance, design, or multiverse, the conclusion remains the same. The existence of atoms is astonishingly contingent. The conditions required for them to exist are so precise, so interdependent, that their presence in our universe is nothing short of a cosmic miracle. And what a journey those atoms have taken. Forged in the hearts of stars, they've been scattered across galaxies, gathered into planets, dissolved in oceans, and eventually woven into the complex biochemistry of life. Some of them now sit inside the neural circuits of your brain, enabling you to read and ponder these words. The atom, that most elementary unit of matter, is the cornerstone of a vast and intricate story. A story of precarious balances, improbable coincidences, and profound implications. It is the narrative thread that runs through physics, chemistry, biology, and consciousness itself. As we gaze deeper into the cosmos, as we delve further into the quantum realm, we are reminded again and again of how rare and precious our existence truly is. And perhaps, in the end, it is this very improbability that makes the story of atoms and the story of us so endlessly compelling.